In our world, teeming with life, there are particles too small for the eye to see. Some can pose a threat to our respiratory systems. Humanity has engineered a remarkable defense, the respirator. This device acts as a personal guardian. It is a filter, a barrier against unseen dangers, designed to create a seal against the skin. Whether on a construction site, in a hospital, or a polluted city street, the respirator offers cleaner air. The purpose remains the same: to provide safer air to breathe. The air we breathe is fundamental to life itself. Each inhalation brings oxygen, the fuel that powers every cell in our bodies. But air is not always pure. It can carry a multitude of passengers: dust, pollen, tiny droplets from a cough or sneeze, or even microscopic industrial byproducts. Modern life and certain environments present challenges that natural defenses cannot always overcome, making external protection essential. Tiny particulate matter, often referred to as PM2.5, can penetrate deep into the lungs. From there, it can even enter the bloodstream, potentially causing a cascade of health problems. In workplaces where dust, fumes, or chemical vapors are prevalent, the risk is even greater. Here, respirators are not just advisable, they are a critical line of defense for workers' long-term health. In healthcare settings, respirators, particularly high-filtration ones like N95S, are indispensable. They protect the wearer from inhaling infectious droplets and aerosols. Beyond specific scenarios, the general quality of air in many urban environments is a growing concern. The effectiveness of a respirator lies in its materials. Each component is selected for its specific properties, contributing to the overall function of filtration and comfort. The most critical material is non-woven polypropylene fabric. This synthetic polymer is transformed into a web of fine fibers. These fibers are not woven like traditional textiles, but rather laid down in layers. This creates a complex, tortuous path that airborne particles find incredibly difficult to navigate. Polypropylene is favored for several reasons. It is hydrophobic, meaning it repels water. It is also relatively inert, ensuring its stability. Furthermore, polypropylene can be processed to create fibers of varying diameters, some incredibly fine. These fine fibers are crucial for a process called electrostatic charging. During manufacturing, these layers are imbued with an electrical charge, turning them into powerful electric filters that actively attract and capture particles. Another key material often found is melt-blown polypropylene. This layer is often the primary barrier against the smallest and most penetrating particles. While the filter media are the heart of a respirator, other components are essential for its proper function and comfortable use. Consider the head straps. These seemingly simple bands play a crucial role in achieving a secure seal against the face. They are typically made from elasticated materials such as braided spandex or thermoplastic elastomers. The material must be strong enough to hold the respirator firmly in place during movement and speech, yet it must also be comfortable enough for extended wear. Then there is the nose clip, a small but vital piece. Usually made from a malleable metal like aluminium or a pliable plastic, it is embedded along the upper edge of the respirator. Its purpose is to allow the wearer to conform the mask tightly over the bridge of their nose. Some respirators incorporate an exhalation valve. This is a one-way port designed to make breathing out easier. When the wearer inhales, the valve closes, ensuring that all incoming air passes through the filter media. The creation of a respirator begins with the precise handling of its core materials, particularly the non-woven fabrics. Huge rolls of polypropylene, each destined to become part of a protective barrier, are loaded onto sophisticated automated machinery. These machines are the unsung workhorses of respirator production. Typically, a respirator will consist of multiple layers: an outer protective layer, one or more filter media layers, and an inner comfort layer. Each layer is carefully guided into position, ready for the next stage of its transformation. The process of layering these fabrics is a marvel of automation. Sensors monitor the tension and alignment of each sheet, ensuring they combine perfectly. The machines work relentlessly, feeding the continuous sheets of material forward. It is here that the electrostatic charging of the filter media often takes place. The fine polypropylene fibers are passed through a high-voltage field, imbuing them with that vital electrical charge. Once the layers are correctly assembled and charged, they are bonded together. Ultrasonic welding is a common method for this. This bonding process often simultaneously cuts the layered material into individual respirator blanks. With the layers of fabric fused together, the flat material now needs to be given its three-dimensional shape. This is a critical step, as the respirator must conform closely to the contours of the human face to be effective. For cup-shaped respirators, a common design, this involves a molding process. The multi-layered fabric blanks are fed into machines equipped with heated molds. These molds press the fabric into the desired convex shape, using a combination of heat and pressure to permanently set the form. During this shaping stage, or immediately after, other components are integrated. The malleable nose clip is carefully positioned and secured. Its precise placement is vital for achieving a good seal across the bridge of the nose. The edges of the respirator must be sealed. This is often achieved using the same ultrasonic welding technology that bonded the layers. For foldable respirators, the process involves precise folding and sealing along specific lines. Finally, the head straps are attached. The manufacturing of respirators does not end when the final strap is attached. A most crucial phase then begins: quality control. Given the life-protecting role these devices play, the standards for their performance are exceptionally high. Every stage of production is subject to scrutiny, starting with the raw materials themselves. Rolls of non-woven fabric are inspected for defects. Samples are often taken and tested to ensure they meet the required specifications for fiber density and air permeability. Once the respirators are assembled, a battery of visual and physical inspections takes place. Trained inspectors or sophisticated automated vision systems examine each mask. They look for any defects in construction. Beyond visual checks, dimensional accuracy is also verified. Respirators must conform to specific size and shape parameters. The strength of the strap attachments is also tested. The most critical quality control tests for respirators evaluate their actual performance, specifically their filtration efficiency and breathing resistance. These tests are not performed on every single mask, but rather on a statistically significant sample from each production batch. To test filtration efficiency, the respirator is mounted on a test rig, and a stream of air containing specific test aerosols is passed through it at a set flow rate. Sophisticated sensors then measure the concentration of particles before and after they pass through the respirator material. For an N95 respirator, it must filter out at least 95% of airborne particles of a specific size. If the samples from a batch fail to meet this stringent requirement, the entire batch may be rejected. Breathing resistance is another key performance characteristic. A respirator must filter effectively, but it must also allow the wearer to breathe with relative ease. Tests are conducted to measure the pressure drop across the respirator as air is drawn through it. There are specific limits for inhalation and exhalation resistance. Fit testing is a concept deeply ingrained in respirator design and quality assurance. The integrity of the seal is paramount. The journey of a respirator, from raw polymers to a finished protective device, is a testament to human ingenuity. Each step, from the careful selection of non-woven fabrics to the precise layering and rigorous quality control, is designed to protect the delicate act of breathing. These unassuming objects stand as silent sentinels against invisible threats. In healthcare, respirators are fundamental pieces of personal protective equipment, shielding doctors, nurses, and other frontline workers. Beyond hospitals, they are indispensable in countless industries. Construction workers rely on them to avoid inhaling harmful particulates. Factory workers depend on them to guard against chemical vapors and metal dusts. Ultimately, respirators offer peace of mind and a tangible layer of defense. Ongoing innovation promises even better protection in the future.